And can everyone see my screen? Okay, great. So as you all know, we're talking about hospitals today. I'm Chris. This is Chem Engineering 4870. So we already went over my background, so I'll spare you guys that. One of the first things I want to talk a little bit about is just trying to demystify hospitals, because having been in the industry a little bit, I feel like people in general tend to put hospitals and healthcare on a pedestal in terms of their complexity. And there are a lot of systems, they're really mechanically intensive, there's a lot going on. But they're really just hotels with medical gases, like, to be honest. When you kind of think about the primary function, people stay there overnight. There's these little suites where there's a room and a bathroom adjoining, but there's medical gases going to them. I mean, yes, there are sometimes attached like clinics and diagnostic and treatment centers, we call them, like where there's imaging, so like MRI or X-ray, or operating rooms or other like procedure rooms where they're doing some sort of medical procedure. But by and large, just kind of relax and think about them like a hotel, with some other ancillary systems. That said, I think it is worth talking about some consequences, and making sure that as engineers, we all measure twice and cut once, and like exercise some caution in what we do, because there are people who have jeopardized health, or complicated things going on. So there's particularly be careful around NICUs, which are neonatal intensive care units where there's little premature babies, operating or procedure rooms. Those have really a very large infection control risk when people are open, and they need to be sterile. Cancer treatment units, or like bone marrow treatment wards, because people who are on chemotherapy drugs and have had bone marrow treatments often have pretty compromised immune systems, so they can't fight off infection. So you have to be careful that you're like positively pressurizing those spaces, things like that. So I don't think it's worth going into all those things today. And but just keep in mind like a healthy respect for what you're doing. Next thing is, why hospitals? Why have Julie and Mariah and Cody decided to put this on your syllabus? And I didn't talk to them about this, but I'm gonna go out on a limb and think that I know why. And that's because hospitals are incredibly energy intensive. And in particular, we can do something about why they're energy intensive. About 50 to 75% of hospital energy use, depending upon the hospital, is consumed in the HVAC and the water heating systems. So optimizing these systems can yield a pretty immense energy savings opportunity, I'd say in the neighborhood of 5 to 20%, without even replacing equipment, like without quote unquote capital measures, just recommissioning and tuning up. That's not really a, if you've been in energy efficiency for a while, that's not really a surprise to hear any of those numbers, I don't think. But I think that the thing that's often overlooked in healthcare energy efficiency and optimization is trying to just apply rules without really understanding how the mechanical systems work. And I mean upstream and downstream, because there's often kind of layers to the heating and cooling systems, which we'll get into today. So as such, I want to focus the first part of the presentation today on kind of understanding what are some of the fundamentals of these HVAC systems and what's the most common configuration. So today we're going to focus on VAV, or variable air volume reheat systems with central air handling and central chilled water and steam generation, because that's how pretty much most modern hospital design is handled, and most of what you guys are likely to encounter in the field. And then again, here's a quick outline as well. We're going to talk about systems. I'm going to cover a couple of common energy conservation measures, or ECMs, and then we'll talk very briefly about what I didn't cover and what could be kind of future learning for you guys. So the first one, the central plant, we're going to start at the larger system and then kind of move all the way down to the zonal, the single system level, serving just this one small space. So first thing, central heating plant. This often in older hospitals is the center of the system is usually a steam boiler, which you have down here in purple. There's often steam lines leading all over the hospital campus, going to like shell and tube heat exchangers, like you see here in orange, for generating maybe domestic hot water. Maybe they're generating heating hot water for heating as an HVAC heating to heat the building. Or it might be going to the large central kitchen to heat steam kettles for cooking food, steam to sterilizers, where they're sterilizing and processing instruments for surgical procedures. Domestic hot water, just generated down there that gets thrown out to all the bathrooms and lavatories. Heating hot water is going to HVAC type equipment like air handlers, or not shown here are VAV boxes. Steam humidifiers for directly injecting steam into air distribution systems, so that the air isn't too dry and you're maintaining kind of controlled humidity in the space. And that does show absorption chillers, but honestly, this is a canned graphic. Those are pretty uncommon, so I'd say ignore that. The next part of the central plant, or the central utilities on a hospital campus, is the cooling system. So this is typically a chilled water system where there's water that is cold or chilled that's pumped around the hospital campus in a closed loop. So this schematic here is like a simplified schematic with just one air handling unit, one cooling tower where you're ejecting the heat by evaporating water, and one electric chiller that has a refrigeration cycle to cool the water that's on that closed loop going to the air handlers. But by and large, what's happening is you have this closed loop going through the evaporator side of your electric chiller that's cooling air going through an air handler. This air handler might serve one floor of a building. It might serve an entire building itself, like a whole tower. Totally depends. But that air handler is removing heat and air conditioning. That gets pulled out through the chiller, lifted to the condenser water temperatures, and then rejected as water vapor out of the cooling tower. So here's another schematic just to illustrate a more complex configuration, but what's honestly more common. And as you guys are auditing hospitals, this is probably more what you're going to see: a multi-chiller chilled water plant and a multi-air handler distribution system. Also, one thing to note is that you have two chilled water loops and two separate hydronic pumping systems here. You have a pumping system called the primary loop that goes through the chiller or the source equipment. And you have a secondary loop and secondary pumps that actually move the water from, usually from the central plant out to your loads, the air handlers in this case, and then back. And then you have this, they call it a balance pipe here. People also call it a bypass that kind of hydronically decouples those two systems. Next piece is, this is a zoom in of what's going on inside of one of these air handlers here. So you have air handling units. So air handling unit is, I like to think of it actually as just a dumb box with a bunch of components inside to accomplish 3 different tasks. The first one is ventilation. So to circulate air through the building, it's the fan in the air handling unit is what's actually pushing the air like through the space and circulating it into rooms. Next one is filtering the air, so that you don't get particles from your outside air, like getting thrown into the space like dust or lint, lint from return air. And then the last thing is conditioning. The third thing is conditioning the air. So we have a heating coil if it's really cold outside, that you're not throwing, winter day 30, 40 degree air into your space in the name of ventilation, or cooling, that if it's, hot outside, that you can cool that water down or that air down with chilled water from your central plant. So those central utilities we talked about, the heating plant generating steam and heating hot water, and the chilled water plant generating chilled water for cooling, kind of integrate into the air handler here by delivering liquid to this closed heating coil and closed cooling coil as air moves across it. You can think of those coils, I didn't include a picture here, but like a radiator in your car, where it's liquid running on one side and then a finned coil with air running across it. So then downstream of your air handler, you have VAV reheat boxes in this scenario. So a VAV box usually serves, we call it a single zone. So that's usually a few spaces within interior walls. So in a hospital, it could be, there's usually only one patient room per VAV box. The patient room and the bathroom are usually on one box. And when you're walking through like a commercial building or a hospital, anytime that is a VAV system, anytime you see a thermostat on the wall, there's a VAV box associated with that thermostat. It's a 1-for-1 relationship with the thermostat to the VAV box. But it's a many-to-one relationship between a VAV box and your air handler. And that's shown in this purple diagram down here. So in this diagram that's outlined in purple, these components here are actually your air handler, the heating coil, the cooling coil, your supply fan, and then these dark black lines are ductwork delivering air to your VAV box, which is right here. So VAV box has a damper. That's what that little line means. So damper is, familiar with cars, it's almost like a throttle body. So it's just a flapper in a piece of ductwork that kind of, it's a valve that is controlled by a little motor, and it opens and closes to modulate the amount of air that goes into the zone here downstream. And then also working in conjunction with that damper is a reheat coil. That's what RHC stands for, reheat coil. So that's a hot water coil, also served by one of those hydronic hot water loops that has a valve on it that modulates to the space temperature. So in red up here is kind of a more detailed schematic of a single VAV box off of the supply ductwork. So again, you have a damper on a little motor. Oop, let me go back. And a coil with a valve. And those are working in conjunction with a little controller, which is basically a computer to control your discharge air temperature and volume into the space or your zone here, so that whatever or whomever is in that space is comfortable and ventilated.
Sorry to interrupt, Chris.
Yeah.
Can I say something? Yeah, I think we have a problem in our Zoom. It says that it will end 5 minutes and it needs to upgrade. Can anyone help me to increase the length of this meeting? I have no idea. How can I do that?
We can just turn off the meeting and I'll meet back up really fast, and it should last for another 40 minutes.
Oh.
I think this might be because you used a personal Zoom account
Yeah,
for this meeting rather than the U of U account.
Yeah, I think that's the problem. So can we leave and sign in back?
Yeah, is that okay with everybody?
Sorry, so sorry, guys.
Okay, no problem, Allie.
If you put the new Zoom meeting link in the chat right now, that way we can all have it before we leave.
Yeah, sure. So
Thanks for the pause, Chris. Looks like we're
Yeah.
just at a
No
good
problem.
point.
sorry.
So
So
Yeah. My screen.
yeah.
yes,
Yeah.
Okay. Thanks. So now we've gone through a system overview. Now I'm going to go over some of the most common energy conservation measures I'd recommend you guys keep your eyes peeled for as you do your audits. So the first one is to remove overrides. So there's kind of two different ways I'd go about looking at this. The first one is probably the most important one, and that's checking the building automation system, aka the controls or the BAS, the BMS. But those all mean the same thing. It's the centralized computer control system that runs the whole HVAC and sometimes the lighting and other systems in a hospital. So if you get with a controls technician, it varies based on what sort of building automation or controls platform you're working on, how to do this. But if you get with a controls technician, they should be able to help you run an audit, like basically a report that pulls up any sort of overrides. And this is key because two reasons. One, there's a huge human factor here that often operators, people who run the system day to day, set some sort of override because something happens 15 minutes before they had to leave for the day. And then it gets left that way for years. I kid you not. The other thing though is that often these overrides indicate things that are broken and require fixing and something else to get to the root of the problem. That's the more computer-centric way. The other thing that you might see and is worth looking at is these are motor-driven systems largely, the pumps, the fans, the compressors, and when you go back upstream of those motor systems on the power side of them, that there's some sort of switching usually. And I have a photo of one of the slightly older school types of switches. It's called an HOA, stands for hand off auto. And it's kind of the non-computer way of putting something in override. If you turn it auto is where you have a control system, some automatic system switching it on and off or modulating it. Hand is, it runs all the time. It never shuts off, runs at full speed. So those are kind of the two places to look. And where we go with this is that it usually requires fixing the root of the problem. And the root of that problem is broken stuff.
Chris,
Yeah.
actually, I'm going to jump in really quick because I mentioned early on that we have 4 brand new people today, and
Okay.
we have asked them to hit the big red button when we talk about acronyms that don't make sense. So I just want to connect something really quick here for the team, that Chris's term ECM is equivalent to the IAC's term AR. So basically ECM stands for energy conservation measure, whereas it means the same thing, but we will typically use that AR, our assessment recommendation, as the equivalent term. So thanks, Chris. Just wanted to jump in there.
No problem. I love my acronyms, so guilty as charged. So the second one that usually ties back to that first one is fixing broken stuff. And this is a bit glib, but these are mechanical systems. And so that means things move. And if things move, they're eventually going to break and wear out. So the two most important places I would look would be Airside Economizers. So in our little air handler schematic here, those are signified by these kind of diagonal lines in these solid lines, and those are physical dampers. And so what those are going to look like when you go to the field is this device on the right side of the screen here. That's the actuator. And then these silver kind of parts connected with a rack here are the actual damper blades. Those can get bound, the actuator can be broken, can be disconnected, wiring can be chewed through. There's a myriad of things that could happen, but those often don't work. And when they don't, they waste huge amounts of energy because you could be pulling in too much outside air at the wrong times when it's really cold outside or really hot, or you could not be pulling in any outside air. The next one is leaking air handler. AHU stands for air handling unit. Chilled water or heating water or glycol heating water valves. So this means the valves here, there's control valves that are modulating on this air handler to modulate the fluids that go through these coils so that you're controlling the temperature of air leaving the air handler. And those valves are mechanical. The actuator can break. The valve, the metal part inside or brass parts can actually wear out, and fluids can leak by because there's pressure behind that valve all the time. When that happens, you're wasting energy. So, you can look at those on the controls based on temperature to see if things are leaking. Another way is if the controls say that those valves are closed and you're in that mechanical room, do this with caution, but use your hands, use your senses. Gently, very carefully touch something or shoot it with the temperature gun. Hopefully you guys have one of those. If it's hot or cold and it shouldn't be doing any conditioning, the valve is leaking. ECM3 is simply turning things off. And to get a little bit more specific, want to talk about scheduling. So scheduling is simply the matter of usually through the control system, putting equipment on a time clock. So at the same time, every morning or night or same days of the week that things turn off. So in a hospital, a lot of people will might walk up to a hospital and say, "Oh, hospital never closes. It's open 24/7. You can't schedule anything off." And there are many things you can't schedule off, but that's quite frankly painting with too broad of a brush. There are the medical office or office buildings or clinics. They're usually attached to a hospital. Those are not open at nights often, and those are not open on weekends often. There's administrative spaces like the engineering building, or maybe the outpatient x-ray department isn't open on the weekends. There's non-clinical support spaces. And then there's even simply conference rooms. A lot of non-essential staff aren't there on the weekends and nights, and so conference rooms aren't really used. When you're looking at scheduling those, there's a few things. There's scheduling the zonal temperatures, which is hopefully you guys all do setbacks on your house or your apartment yourselves right now. This is the same as that. It's widening the deadband that you're heating or cooling a space. But the next one is zonal ventilation minimums. Those VAB boxes we talked about here never fully shut during an occupied state. They're always letting some air into the space so that there's fresh air. So you're getting some of that outside air and fresh air into the space. But if there's no people in the space, you can schedule that off, and you can schedule that damper to fully close and that amount of air to zero. There's nothing wrong with doing that. Next one, let me check the chat. I see a question.
It's just me reaffirming your point.
Okay. Thanks, Julie. If you can, you have to get lucky on this one, but if an air handler serves an entire piece of a building or the entire building that is fully unoccupied for a period of time, you can schedule that entire fan off and just kill all of the airflow and therefore all the conditioning. But quite frankly, that's pretty tough to find. And in Utah's climate of extremely hot in the summer, extremely cold in the winter where you have a freeze protection problem, I've always been a little bit gun shy about that, to be honest.
Chris, I have a question.
Yeah.
In addition to just scheduling it based on like a fixed occupancy schedule,
Mhm.
is it common to tie controls to like real-time occupancy measurements, like having an occupancy sensor in individual rooms? We just visited a hospital last week and it was in Blanding, so a pretty small facility in rural Utah.
Yeah.
They had 2 patients in the hospital at the time we
Yeah.
visited.
Yeah.
But they basically control all the set points as if every single room is occupied. So how hard is it to, like, if there is a patient room, for example, tie that to occupancy where it would time out and if it doesn't detect anybody in the room, and relax the set points, and then maybe once a nurse comes in to prep the room or something, it says, oh, somebody's here, and kicks everything back on? Is that too risky for a hospital?
So there's potentially 2. I've never done it in patient rooms. My team at Intermountain, like we always talked about the possibility of tying the actual scheduling of some of those rooms and occupancy and the HVAC system to like the nursing system. But getting IT to talk like all the way up there never happened. It's pretty tough to get those systems to talk. And you could do it with simply occupancy sensors, like, the ones that turn lights on and off. But has anyone ever had those turn off in the bathroom on them? So in kind of a critical environment with ventilation, it hasn't been something I'd say most engineers are comfortable with. But in those administrative spaces, so offices, if it's a 1-for-1 for the place with the physical walls, and that one box serves just that room, or conference rooms are usually a great example of this. Conference rooms are a great candidate, Cody, for an occupancy sensor in healthcare. I wish there was more applications for them, but that's probably the best one for ventilation. And
the only one I ever saw was on a new construction, and they were using CO2 for demand or for occupancy measurement.
Mhm.
But again, that
Cody,
was from scratch.
We're actually looking into doing some occupancy-based ventilation setbacks at the other hospital we're looking at right now. And they would do that with a dual technology occupancy sensor in their operating rooms. So just to set back the ventilation, because the ventilation code requires fresh air changes per hour, but ASHRAE 170 allows you to go to an unoccupied setback for ventilation. So just when that, and there are dual technologies that use like infrared plus like motion detector or ultrasonic waves or something so if the room is unscheduled or unoccupied, you can reduce the amount of ventilation air. And then as soon as it detects occupancy, it brings the ventilation back up. Is that something that you've seen done before, Chris?
I have. I would say be really careful with that and make sure you can schedule. You absolutely cannot schedule the occupancy airflow to 0 during the unoccupied times, because you still need that space to stay positive to all the surrounding spaces for sterilization purposes. The air is blowing out of that space. You can drop the airflows, but as long as you maintain that pressure relationship, and that is tough to do, but not impossible.
But you can maintain that pressure relationship with recycled air rather than fresh ventilation air, right?
Some of it's going to leak out. I'd say it depends upon the HVAC. Some of it's going to leak out, so you're going to have to let in some outside air. Like,
Okay.
Yeah.
Michael, you're not looking at patient rooms, right, where someone would be staying in a room. The sense that I got was even if you had a really conservative like timeout on the occupancy sensor, like 4 hours or something, because the place we went, it just felt like some of these rooms probably go unoccupied for days or weeks. It just feels so wasteful. But we also don't want to do something that ends up with this getting turned off and, or even worse, some causes some problems.
Yeah, we're looking at operating rooms, which obviously are going to be used all the time, but you can't predict when or how often or for what period. So for those places, maybe an occupancy sensor makes more sense than scheduling.
Bottom line, Michael, is I just don't trust. I don't care what the technology is. I don't really, when push comes to shove, trust occupancy sensors, especially in critical applications.
Me neither, to be honest. Yeah, that's a
very
huge
helpful.
liability. Yeah, and scheduling as well in ORs. Like, yeah, I'd say focus on like if you really want to dig in there. This is one of the additional things I talked about, or I'm gonna talk about at the end, but like go through the ASHRAE 170 calculation for that space for what the ventilation rate should be. If you have a recent balancing report for that operating room, and make sure that it's not like excessively high air changes during the occupancy time. I mean, ORs need to be minimum 20 air changes per hour, and there's plenty of times that they're above 30 if no one's really looked at it, and that's pretty excessive and wasteful. So, you know, maybe as kind of a compromise, could be somewhere to look in like an OR.
So Brooke and Paula, I hope you're listening to this conversation. Our RAR on occupancy sensors in patient rooms might not be a go, but we'd want to look at those rooms that are just like the Monday through Thursday daytime only, and make sure that we're relaxing set points on a schedule in those.
Yeah, nice. Okay.
Chris, I just want to jump in. Really great discussion. Love it. And also wanted to say, if folks need to go, please feel free. We'll continue to record your presentation. Our class is technically scheduled till 5, and I know some people have some hard commitments now, but we'll keep going and finish out. And if folks want to stay, I definitely encourage you to do that. Thanks.
Sounds good. I have 5 more slides just for those that are on the fence. So the couple quick things I want to mention, then we'll be off of this, is when you're scheduling, particularly like the zonal temperature set points, looking at the asterisk down there, consider thermal inertia. And what I mean by that is, you know, if people are going to be in that space at 8 o'clock in the morning, you can't have the temperature schedule click over right at 7:59 and not expect complaints. So, you know, you probably need to build in maybe an hour of buffer of that system to ramp up and like bring the space up and down in temp. The other thing to think about in terms of temperatures is on the other side too, is often you could kill it on the other end right at the time that people are standard leaving, and it will take a while to drift and become uncomfortable. And then enable and disable set points. So where to look, seen plenty of chiller plants that run all winter and there's no actual load on them. They're pumping chilled water. The chiller is beating itself up, cycling on and off because there's no load. So look at enable, disable set points, whether that's an outside air temperature or something like that. And that kind of applies down to the water side economizer as well, which is part of the chilled water plant. ECM4 controls retrofits. So what, probably making some of your head spin. What are controls retrofits? So some background is how mechanical engineers design systems is for what we call design day. And that's the worst case scenario for needing to heat a building, or worst case scenario for needing to cool a building. So that's in Salt Lake. I want to say design day for heating is about 100 degrees, or for cooling is about 100 degrees, and for heating it's probably about 8 degrees. So the other 99% of the time we're somewhere in between there, and yet our systems are sized to do that worst case scenarios. So what this means is that we can relax some of these set points that are designed to get us there on that worst design day the rest of the year and the other 99% of the time. So that could be on your variable volume air handler, the static pressure set point. That static pressure is what gives pressure to create flow down the ductwork. And but if you don't need full flow because it's not a 100-degree day, you can relax that static pressure set point by looking at the VAB boxes and then set that back. Same thing with the discharge air temperature. If it's not 100 degrees out, you probably don't need 42, 45-degree discharge air temp. It could be much higher. Same thing with chilled water plant. You want those supply temperatures to kind of reset between 42 and 52 degrees Fahrenheit. Chilled water differential temperature or differential pressure between 10 and 25 feet water column. Big caveat on that, that's going to be very system specific on where your sensors are located in that case. And heating hot water plant, that's going to be 120 to 190 degrees. That also, I should have put an asterisk on that because that's very system specific, because if you have a condensing hot water boiler system versus a low pressure steam system, it could be much higher or lower if you're condensing boiler versus steam. The fifth measure is Vab Box Optimization. This is a little bit more advanced. It's now energy code that VAB boxes are supposed to run this way, where they don't just constantly deliver the same volume of air all the time, that damper really modulates. So there's, in this diagram we have here, there's a temperature and correspondingly a controlled dead band. You know, if your set points for heating and cooling are, we said 68 to 73 degrees in your zone, that you're then in that dead band if the temperature is 70 degrees. And so that means you're just giving the minimum airflow, so the ventilation minimum, and it's going in there, but you're not opening your reheat valve at your VAV box. But then as cooling demand increases, this solid dark line is your damper in your VAV, that your airflow increases to meet additional cooling load. Correspondingly, if you have a heating call and your heating loop starts to increase, then the first measure is this solid line that your supply air temperature, or this dotted line, your supply air temperature increases by opening that hot water valve. So you keep the same amount of airflow, but just increase the amount of hot water going through the coil to increase the discharge air temperature. And once you hit a maximum discharge air temperature and you still need more heat to hit your set point, then you start opening your damper and then also opening your valve as your damper is opening, because you're going to have a higher load, but keep a constant temperature. This is, I don't expect you guys to get your head around this the first time, because this is not an easy graph to look at. But this is pretty important. And then two other points on your VAB box optimization. The first one is often I've seen many control systems that by default are basically letting that hot water valve open as much as it wants on a call for heating, and getting extremely high discharge air temperatures. So if you have a discharge air temperature that's more than 20 degrees above your space temperature, it's usually not doing any good, because that hot air just rises in the space and it sits on the ceiling, and it doesn't actually like make the occupants of the space feel any warmer. It doesn't mix. You get really bad stratification. So you know, check what the maximum discharge air temp is. I wouldn't want to see it at above 88 or 90 degrees. And then the other one is to schedule those ventilation minimums to 0 CFM during unoccupied periods, which we talked about, which basically means that this line here drops all the way down to 0 airflow if you're in an unoccupied state. Next one are those actual VAV temperature set points. So that's how wide you set your deadband here for heating and cooling. So for cooling, I should also caveat, this really only applies to administrative spaces. Patient spaces, there's often good need that they need to be wider than this. But for administrative spaces, 72 to 75 should be the cooling set point, and 68 to 70 should be the heating set point. Try to get about a 5-degree deadband if possible. And then your unoccupied set points, cooling, you could shoot for 78 to 80, and then heating, I should have dropped that down to about 60. That's a typo on my part, but probably about 60 to 65 degrees. I'll correct that when I send you guys these slides. So that covers the ECMs. This is my last slide of any content, and I want to cover this. These are things that we didn't go into deep dives on, and I touched on slightly, but could be further learning. And I could literally talk for days on some of these. First one is steam traps and condensate management. So if you have a steam boiler, steam traps and condensate management. So that's how you get condensate back from your loads as the steam turns from a vapor to a liquid. Steam traps then separate that vapor and liquid at the load. And then there's usually mechanical pumps or pressure powered pumps to get it back to your boiler plant. So you then feed it back into the boiler, heat it back up, vaporize it, send it back out. Management of that condensate is really important. Those systems fail a lot. They're designed wrong. People don't understand them. It's kind of like a dark art, steam systems at this point, because they used to be in almost every large building. Now they're pretty much only in hospitals these days. So there's not a lot of people understand them, but if you do, you can kind of write your own ticket. And so Spirax Sarco makes steam equipment, and they have these 2 books, the design of fluid systems hookups and steam utilization. They have great background on them. Then the other one is ventilation optimization. We touched a bit on this. So the ASHRAE code for this, for healthcare facilities, is ASHRAE 170. Actually calculating those and running through those and setting those specific to each space can knock a lot off your energy bill. And then third one are LED retrofits. Sure you guys are well aware of that. Like, just do them. If there are major fluorescent systems in buildings, like linear fluorescence, like, they need to just do them and apply the 80-20 rule. There are going to be little custom, like, futsy fixtures, like lighting the donor's light in the lobby, or weird little architectural stuff in the kitchen. And you might think, oh my gosh, we need to come up with a solution for every one of these fixtures if we're going to do a retrofit. But don't do that. Just focus on what is the bread and butter, and those are troffers and can lights, and any sort of linear type lamp, like a tube, T8s, T12s, things like that, even T5s now. And the last one is chiller plant optimization and sequencing. So when you have multiple chillers in a plant, particularly when they're different sizes, this can get pretty complex. And if they're big systems, there's quite a bit of energy you can wring out in different scenarios with how you start and stop those and share load. So I won't go into that, but that's kind of another kind of topic you could go on for. So let's see, have questions in the chat. Question about slides. Yes, I will send my slides to Julie, Mariah, and Ellie and let them get them up there. Let's see.
What a better way to end than on Dilbert.
Say that again, Julie.
What better way to end a presentation than with Dilbert?
Absolutely, yeah. So
Chris, do you have a couple more minutes if people have questions?
I do, yes.
Okay, So I had one sort of general question, but I want to open it up to the whole group that's still here. If you have questions for Chris, by the way, he's coming back next week again, so we'll have more opportunity, but please chime in with questions now if you have them for Chris.
Hi, Chris. I had a question.
Hey, Mateo, go for it.
Hey, so I know you said that for example, patient rooms, it would be really high risk to mess up with the ventilation system. But
Yeah.
what about the temperature set points? Because right now we're working on an assessment for for a hospital, and so the thing is that their set point currently is like from 68 Fahrenheit to 72 Fahrenheit. So I was wondering if we were to install occupancy sensors, if we could maybe say that if a patient hasn't been in a room for a long time, we could just set the set point to a default value, because the patient is allowed to mess up with a the thermostat from 68 to 72. But what if they would just were to leave it at 72 for the whole time? When they would just leave it at 68 instead. So maybe an occupancy sensor to leave it at default.
Mm-hmm. It could. That's definitely much lower risk, for sure. Yeah. I'd say I've always been surprised actually how expensive getting an occupancy sensor integrated in a retrofit scenario actually turns out to be. And so doing that just for a temperature setback in a patient room, I could see that actually being kind of a tough payback, to be honest, because you're not likely going to be able to, you're not really going to be dropping the airflow a whole lot because you're sitting at that ventilation minimum. So, I mean, you might a little bit if you widen the dead band, but I can see it being tough. I'd say it is probably $1,500 to $2,000 to get one of those integrated for a patient room. So think about the cost. Yeah.
Thank you.
No problem.
Thanks, Mateo. Looks like we got maybe 5, 6 minutes left. Is there other questions for Chris while he's here today? Especially those of you maybe doing hospital assessments right now. Okay, well, Kristen, I'm going to jump in with just a couple things to get your thoughts on and comments before we wrap up.
Sure.
The first graphic, or one of the first graphics that you showed, was just the sort of common systems in hospitals. And in particular, I wanted to get your quick take on some of those things that are a little more unique for hospitals that we don't see other places. And in particular, if in your IMH experience, there were successful retrofits. So in particular, I was curious if you would speak to the sterilizers, the food, the steam kettles, or the autoclaves. Did you do ECMs there successfully with any of that or hospital-like equipment?
No.
Is that right?
Yeah.
Interesting.
I would say the biggest opportunity there is if those are on a central steam system, is really running to ground what the steam pressures require at that load versus what's being generated at the boiler. So because this probably almost every hospital in the Intermountain system, when we first started working, when the energy team first started working with them, there was a misconception of, oh, the central sterile with the autoclaves, they need 100 psi, 105 psi, and sure enough, there'd be a gauge that said whatever pressure they needed in that mechanical room on the backside of those autoclaves. And then there'd be a pressure reducing valve knocking it down to something less. And that's really what they needed. But everyone looked above the PRV and said, oh, we've always had 100 PSI. That's what we need to have every time. Looking at, I'd say go to the load, see if there's a PRV, and that's a smoking gun. And it's the same thing for the steam kettles. But the sterilizers and the autoclaves are going to be what are usually driving the campus steam pressure, usually are the highest load, because all the HVAC is like lower pressure, lower temperature. That's usually like 30 PSI steam to 15 PSI. So autoclaves or sterilizers usually are like 60 to 70 PSI. A well-designed distribution system from the boiler to the load, even design day, probably needs only 10 to 15 PSI. So to get it there of loss. So, 75 to 85, maybe even 90 if you put a fudge factor, should be the maximum in a winter day that you actually need of pressure. But most of those low pressure boilers are designed to deliver 120 PSI, and often they get set that way when the hospital opens and no one ever turns it down.
No.
Yeah.
Okay, great.
Do you have, Chris, do you have thoughts on adiabatic humidification instead of direct steam injection? Have you seen those systems used successfully?
I saw those in data centers when I did consulting quite a bit. They're great. But we didn't have those in any of the hospitals. Not being a design engineer, I don't know why, but I think that that's because you have standing water in that in those adiabatic systems usually, and that standing water is an infection control concern in terms of like growing bacteria, and then you're aerosolizing that and sending it into patient rooms for people with compromised immune systems. So I think that's sort of why. I never saw them though.
Okay.
Okay.
Awesome. Anybody got one last question for Chris?
Along the sterilization line, have you ever seen non-steam sterilizers? Like we've heard about some chemical processes or like electrically heated sterilizers.
I think there are some chemical ones that use some pretty nasty chemicals. But there are a few of those in the Intermountain system when I was there. That was driven more by like the specific sterilization process for some weird thing that they needed. Wasn't actually an energy thing that drove it. But since we have less than 1 minute, I'll say the electric piece, they end up usually using resistive heat to generate steam, but they're not bad because then you can turn off your boiler and it's still more effective to just kill it without point of use. Yeah. Thanks, Marat.
Thanks, Chris.